Thanks for coming to my presentation. My name is Gustavo Silva, and today we're going to be talking about the work we've been doing in the Linux Kernel Self-Protection Project over the past 6 years to harden, to add array bounds checking in the Linux kernel. And well, my work in the kernel community has always been supported by the Linux Foundation, and over the last couple of years also by the Alpha Omega project. This project is funded by Google, Microsoft, and AWS. So thanks to those organizations for supporting my work in the kernel. Can you hear me? Well, yeah, okay, perfect. Okay, so a couple of words about me. I've been doing Linux kernel development over the past 9 years. I focus on proactive security. I am a member of the Linux Kernel Self-Protection Project, which is basically the Linux kernel division of the Google Open Source Security team. However, I am not a Google employee. Oh, sorry. Okay, so this is the agenda for today. Well, this is a very, very technical presentation. Probably it's going to take us over 60 minutes. So we are going to start by reviewing some very basic concepts about arrays in the C language. I'm going to explain the work of flexible array transformations we've been doing in the kernel. Then in the main part of the presentation, we're going to see how it is that we've been hardening the memcpy family of functions. And well, we're going to review a recent attribute, the counted by attribute, and a couple of important building compiler functions we use in the kernel. And well, of course, at the end, some conclusions. This is we're going to review a lot of material. I didn't want to add everything in the agenda, but we are going to see a lot more than this. Okay, let's start with the most simple declaration of an array in the C language. What we have here is a fixed size array of 10 elements of type integer. I'm sorry. Something important to mention about arrays in C language is that the language doesn't enforce array boundaries. So it is always going to be up to developers, up to the programmers to make sure that any access to any of these objects is going to be within the boundaries of such objects. An important detail to pay attention here that is going to be important for the rest of the presentation is that the size of this type of objects is clearly well defined at compile time. So the compiler is going to have access to this information throughout the entire lifetime of our application. Now let's review trailing arrays. A trailing array is basically merely an array that is going to live at the end of any structure. So this is a fairly simple example. We have trailing array because it's the last member of our structure, right? Again, an important point here is that the size of these types of objects is clearly well defined at compile time. Okay, now a special type of trailing array is what we call flexible arrays. What we have here is the declaration of a flexible array. Basically, the syntax is with empty brackets, right? That's the difference between the declaration of a flexible array and a fixed size array. In a flexible structure, we are going to say that is a structure that contains a flexible array. One important difference compared to fixed size arrays is that the size of flexible arrays is going to be determined at runtime. Usually, well, I went through this point. Sometimes we need to declare flexible arrays when we don't know exactly how large our array is going to be at compile time. So this is pretty common basically in any C code base. An example of when to use a flexible array is, for instance, if we want to load some firmware, we are developing some driver and we need to load some firmware. Sometimes we don't know how large this blob of data is going to be. So we declare this type of array, then we allocate some heap space at runtime, and that's how we use it. The correct technical term for these types of objects is flexible array members. So flexible array members, they were introduced to the C language in C99. This is because before this, we didn't have a proper way to declare these types of objects. So something important here is that not to be confused this type of arrays with variable length arrays. So this is an example of a variable length array. You notice the syntax is different. So this is something we've been trying to eradicate from the Linux kernel. And actually, we enabled the WVLA compiler option in mainline just to keep this type of arrays out of the code base because they are prone to error. OK, so before C99, people would use one-element arrays or zero-length arrays. So this is just an example of how the declaration of a one-element array and a zero-length array. OK. Again, something important to mention here is that a requirement for the use of a flexible array member is that it should be the last member in any containing structure. And this is actually enforced by the compilers. So a difference with one-element arrays and zero-length arrays is that the compiler doesn't really care if you declare these types of arrays anywhere in the structure and if you use them as a flexible array members at runtime. So in the case of a flexible array, if you were to add another member after this object, the compiler is going to complain, so your code is not going to build. And that's an important point about flexible arrays. Usually, a flexible structure will contain a counter member. In this case, count is that counter member. This member will be useful at runtime because we have a member where to store the size of this type of objects at runtime. So that is how you would use the counter member. So it is important, if you use a flexible structure, it is important to include that kind of member. OK, now let's review real quick how we would use a flexible structure and a flexible array in the Linux kernel, and how we would allocate some heap space for these types of objects. So what we have here is we are calculating the total size for the flexible structure together with a number of items for the flexible array member. And we are going to store that information in total size. Total size is the variable that is going to contain the number of bytes we want to allocate for these objects. Then, of course, we allocate, we call kcalloc, we allocate that number of bytes. And at the end, if you notice, we are updating the counter member with the number of items we want to allocate for the flexible array. However, in the kernel, we don't like that kind of open-coded arithmetic, particularly because when it comes to allocating heap space, it is prone to integer overflows. So instead of that, in the kernel, we would use the struct size helper. What this helper does is that if we detect, well, if we have an integer overflow, this helper is going to saturate to the maximum value that can be stored in size t. Size t is an unsigned integer type. Depending on the architecture, it can be an unsigned integer or an unsigned long. So struct size is going to return a very big, a very large value. And when this value is passed to any of the allocations functions, well, basically the allocation is not going to proceed. The function is going to fail, right? The allocation is going to fail. And that is what we have to mitigate integer overflows during memory allocations in the Linux kernel. These kind of helpers, we have more helpers. We have array size. We have helpers that are going to help you to multiply values, but they are going to detect buffer integer overflows. I'm sorry. OK, so back in the day, this was probably like 6 years ago. I was going through the whole kernel tree, and I was looking for those instances of open-coded arithmetic, and I was actually doing struct size transformations in the kernel. So while I was doing this, I ran into this piece of code. So what we have here is a zero-length array in the middle of a structure, and the issue with this code, when I was reviewing it, was that I realized that this array was being used as a flexible array at runtime. this is some heap space was being allocated for this array, and at the moment something is written into this array, well, the following adjacent member, which is RCU head, is going to be corrupted. So this is undefined behavior, and this is a bug. So the solution here, there are a couple of solutions for this kind of issues. One of them is just merely moving the zero-length array at the end of the structure, and that would be enough to fix this issue. However, if we also transform this array into a proper C99 flexible array member, well, the next time someone else comes and introduce the same bug, the compiler is going to complain, right? So these kind of issues are going to stay out of the Linux kernel. So that's why I decided to transform this into a flexible array member. So then what happened the next time? Then when I was doing my research to know when exactly this bug was introduced, I realized that this issue was there in the wild for 8 years. So this was introduced in 2011, and I discovered this in 2019. So the next thing that I did at the time was to talk with Case Cook, which is who is the leader of the Linux Kernel Self-Protection Project. So he was concerned about it, and at the time we considered that it was important to go and take a look across the whole kernel tree and look for every single instance of these issues, right? And fortunately, we didn't have many, I think just a couple. But what we decided to do at the time was to transform any instance of one-element arrays or zero-length arrays into flexible array members, precisely to keep these types of issues out of the Linux kernel, right? So that's how we started the effort of flexible array transformations, and this took us like probably 5 years to complete. It's not that simple. I mean, this fix might look very, very simple and trivial, but we are about to see why that is not the case. It's not as simple as just removing the 0 or the 1 from the declaration, and that's it. There are a lot of other implications, particularly when we want to transform one-element arrays into flexible array members. Later in the presentation, we are getting into those details. So up to this point, well, I'm going to stop talking about flexible array transformations up to this point. We are going to converge later on in the presentation. We are going to see how this effort became crucial at some point. And we're going to get into other details. So I don't know if you remember back in the day, this was in 2020, I guess. A security researcher at Google, he discovered a set of 3 vulnerabilities in the Linux kernel. At the time, he decided to call them the bleeding tooth vulnerabilities. I don't know if any of you know about these vulnerabilities. Are you aware of this? Okay. What we are going to review here is the bad vice vulnerability. This is one of the 3, but this is pretty illustrative. Okay, what we have here is we have a structure, and if you notice, we have a fixed size array in the middle of a structure, right? And the size of this array, again, compared to the examples in the beginning, the size of this array is going to be clearly well defined at compile time, right? So the compiler is going to have the information about the size of this object at the moment we build our code, right? And on your right-hand side, you can see that we are trying to copy some data into this fixed size array. And the problem here is that we are not checking that the number of bytes we are trying to write into this fixed size array is at least as big or as large as the maximum number of bytes that it can contain, right? So there is no any sanity check here, and well, that is a problem. So what happened here is that the researcher, he was speculating about the possibility of overwriting this fixed size array up to the point of corrupting the next pointer, the list head next pointer. And what happened is that he actually managed to corrupt this object. So based on what we have reviewed, the basic concepts we have reviewed about fixed size arrays and this issue, what do you think is the problem with functions like memcpy, for instance? Well, it might well be the case that memcpy is a pretty naive API. Similarly to the case of any fixed size array, we need to take care of making sure that if we want to read from the source object, we are not going to read beyond the boundaries of this object, right? So internally, the memcpy function doesn't contain any kind of hardening, right, or any kind of sanity check. Also, in the case that when we want to write something into the destination object, we as developers need to take the responsibility of checking the boundaries of those objects, right? So, based on this, what do you think was the fix at the time for bad vibes? It was actually a pretty straightforward fix. Exactly, yeah. We just needed to check the number of bytes we wanted to write into this fixed size array, right? So at the time, this patch was the fix. So now let's review some of the internals, so memcpy. We are going to review a 45 version of memcpy, and let's see how this works. Okay, this is the 45 version of memcpy we had at the time. This is even before bad vibes, right? So here, what we have here is the workforce of memcpy is a building compiler function, the building object size compiler function. So how this compiler function works is we're going to pass a pointer to an object, and this function is going to return the size of the object this pointer is pointing to, right? So this is how we are trying to determine the size of both destination and source objects. Then we are going to check if the number of bytes we want to read and write from these objects is a constant. If that is the case, at compile time, we can immediately determine if we are going to run into a read or a write overflow. If the number of bytes we want to write into our destination object is not a constant, well, we are going to proceed to check this at runtime. And if everything is correct, well, we are going to follow through all the way to execute the actual memcpy, right? Okay, so now let's get into the details about how building object size works. Okay, so for the purpose of this presentation and for the purpose of the hardening we are doing in the kernel, we are going to review a couple of modes for this building object size function. There are actually 4 different modes, but in the kernel we've been using mode 0 and mode 1. Okay. The first argument is going to be a pointer to an object, right? And the second argument, in this case, if we pass a 0, which is the mode 0, this building compiler function is going to return the size of the object from the beginning of the object up to the end of the outer structure. We're going to see some examples, so this is clearer. And if we pass mode 1, this building compiler function is going to return the actual size of the object. Okay, let's review some examples so this is clearer. Okay, what we have here, well, we have a struct-foo and we have a number of members in this structure, and we are going to pass a pointer to the first member to count. In mode 0, this compiler function is going to return 16 because that's actually the size of struct-foo. That's the number of bytes from the beginning of the counter of count to the end of struct-foo, right? But if you notice, an important difference is if we pass mode 1, we are going to get the size of the object, right? Similarly to the case of the name array, if we call this building compiler function and we pass mode 0, it's going to return the size from the beginning of the array to the end of the structure. And in the case of mode 1, it's going to return the actual size of the array. So that's a crucial difference. In the case of flexible arrays, this function actually cannot determine the size of these arrays, and this is actually correct because, well, the size of these types of objects is only going to be determined at runtime. So it is fine that this function is going to return -1, which basically means I don't know how big this object is. Yeah.
But shouldn't be there a pointer to the flexible array which will be populated at runtime with the actual memory?
But when you declare these objects, you don't know the size of the object. I mean, you know.
But you know the size of a pointer to the object because it's a memory pointer.
Yeah, but oh my God, my bubble just came off. I'm sorry. Yeah, but the intention is to return the size of the object. So you're passing a pointer to the object, but that is not enough to determine the size in the case of a flexible array, because that information doesn't exist at compile time. Yeah.
Where is the? But if I just then at runtime allocate.
Oh yeah, no.
The memory.
We're going to get into that. Oh yeah, okay. Let me mention this. This built-in compiler function is this works at compile time. Yeah. There is another built-in compiler function that we are going to review. That is the one that we are going to use at runtime.
I see.
So I'm going to get into that. Yeah. Okay. Thank you. Thanks. Okay. So based on this information, let's remember that the 45 version of memcpy. Oh my God. The 45 version of memcpy at the time before bad vibes was 45 with built-in object size in mode 0. So at the time when this security researcher was doing his work, he didn't actually build a kernel with this fortification enabled. But even if he had done that, this wouldn't have been enough to prevent this kind of vulnerabilities, right? So yeah, at the time there was nothing we could do about it. Okay, so but now this begs the question, because this is the story for what's coming. I noticed that I read the write-up and I shared this on Twitter, and then Case Cook noticed that tweet and he went through the whole write-up and he was like, okay, but the compiler has that information. I mean, why is that we cannot actually prevent this kind of vulnerabilities right now? So he was a bit pissed off, and he started digging more into this. And well, what happened was what I'm about to tell you. So what is something that we could do in this case? Well, the sensible answer based on what we have reviewed about building object size is that instead of mode 0, well, why don't we use mode 1, right? Because if we use mode 1, we are going to get the size of the array, right? And we are not, we can sanity check the size of the array, and we are not going to allow for the write to happen, right? And yeah, actually that is the fix for memcpy. And that is enough to prevent all these kind of vulnerabilities, right? And yeah, life is beautiful, right? Okay, but there is something that we call internal cross-member overflows. So this is a pretty common thing in any C code base. So let's review some code. Basically, what we have here, we have 3 fixed size arrays. And what is going on here is that we are writing, this is actually kernel code, and what is going on here is that we are writing across the whole, the 3 arrays at once, right? We take the address to the first array, and we calculate the size for the 3 objects, and we just call memcpy, and we are writing across the 3 objects, right? So if we enable, instead of using building object size in mode 0, we use in mode 1, this is going to cause a warning, and this is going to be a false positive for memcpy, because memcpy is going to report that we are running into a write overflow. However, this code is correct, right? I mean, for the maintainer, this code is correct. So there is at the time when we changed from mode 0 to mode 1, we ran into hundreds of these kind of false positives. So we needed to do something more, right? It was not that simple as just merely changing from 0 to 1 in building object size. Okay, so there are some things we can do. Well, before that, let me address the problem of false positives in the kernel. Usually, when we work on enabling this kind of hardening mechanisms, we are going to run into hundreds of false positives, sometimes even thousands of false positives, and we are going to explain one of those cases at the end of the presentation. And this is a problem when it comes to hardening any C code base. If you want to enable any hardening mechanism across the whole code base, you need to account for a lot of false positives, and you need to find ways to fix them, right? Otherwise, people, at least in the kernel, they are not going to accept our hardening changes. So in the kernel, in the Linux Kernel Self-Protection Project, we say that we allocate that pane. So what happens with false positives is that they usually are a signal for weak or buggy code patterns, right? And we are going to review some of those patterns. So yeah, in the kernel, in this project, we allocate the pane of fixing all those issues. So yeah. So let's go back to review this code. So one of the things that we could do is, well, we can enclose these three objects in a substructure. And then we can use that a new identifier, and through that identifier, we can access the three objects at once, right? However, if there is other code that access these objects directly, then we need to modify, we need to update a lot of code, because now there is an identifier in the middle, right? So that is something that is not appealing for a lot of people in the Linux kernel. They consider that code churn, so they don't really like that kind of solution. Because yeah, if we want to access, let's say, key material, we would need to go through the new identifier first, and yeah, that's a lot of code. Okay, in the kernel, in the kernel self-protection project, what we did at the time was we came up with the idea of struct group. We're going to review how this works. This is a family of helpers. And what is going on here is that we use this macro. And what this macro allows us to do is to access each one of these objects directly or through the new identifier, right? So the couple of lines at the bottom are equivalent. So that is an advantage of this helper. And let's review the internals. So first, let me tell you that this was created by Case Cook and Keith Packard, which is a friend of the Linux Kernel Self-Protection Project, which happens to be here. Hey, say hi. Yeah. So how this works is it's very simple. We have a union, and we have an anonymous union, an anonymous structure. And thanks to that anonymous structure is that we can access any member within struct group directly, right? And we also have, we create a name for the whole group. And thanks to that name is that we can actually gain bounce checking, right? Because now the compiler has an identifier for the whole group, and it can actually check how big, how large this group of members is. Okay, so yeah, that's how we would fix this kind of issues, these kind of false positives. We would use struct group, and we don't even need to calculate to do this open-coded arithmetic to calculate the size for the three objects, because basically we can just apply the size of operator to the new identifier, and the compiler is going to know how large this object is. Okay, so thanks to the invention, to this innovation, to struct group, and thanks to the change from mode 0 to mode 1, well, now we avoid all these false positives, and we are able to modify memcpy, and now we can use a building object size in mode 1. So yeah, that would be the change, and yeah, life's still beautiful, right? So yeah, at the time we were really happy about this, because this was really a problem. I mean, it was a problem that we knew that could be fixed fairly easy. But the story is that the reason why we didn't use building object size in mode 1 from the beginning is precisely because of this kind of false positives, right? So at the time, people thought that it was too much of work, and no one wanted to do anything about it. But after Bad Vibes, well, we needed to come up with a solution for this. Okay, so we were really happy, and then something really bad happened. Okay, let's go back a little bit and let's review again how building object size works with flexible array members. Okay, again, if we want to determine the size of a flexible array via building object size, well, that's basically not possible. Well, this was not possible at the time. Now, let's review how we would use a flexible array when we want to copy some data using the memcpy function into this array. Okay, so as I was saying, building object size in these cases is going to return -1. This is going to saturate destination size. And well, basically, flexible array member is an object of incomplete type, so we don't know the size of this object, right? So when building object size returns this pretty big value, basically this condition is always going to be false. So any sanity checking is not possible for flexible array members at this moment, right? Well, at the time. And well, the memcpy function is going to proceed. So if we want to write, if we allocated, I don't know, like 100 bytes for the flexible array member, and then we want to write 101, the memcpy function is going to do that. Because at that point, at that time, we didn't have any mechanism to prevent that. And well, this is expected behavior. And this is what was really disturbing to find. Let's remember our trailing array from the beginning. Let's go over this again. As I was saying, the size of this object is well defined at compile time. So the compiler knows the size of this object, which in this case, let's say, is going to be 40 bytes. However, when we were playing with memcpy and trailing arrays, we realized that the building object size compiler function was returning -1 for any trailing array. So it doesn't matter the size of the array. It doesn't matter if it was a fixed size array or a flexible array member. This building compiler function couldn't determine the size of this object. And that was at the time what was really frustrating, because as we have seen, this information is available to the compiler, right? So yeah, basically any trailing array of any size, this building compiler function was going to return, I don't know how large this array is. So the problem is that under this scenario, we were not only incapable of having sanity checks on flexible arrays, but we couldn't determine the size of any trailing array, right? And that was a big problem. Okay, but let's see why. Why was this the case? What we have here is a piece of BSD code. We have the infamous socket address structure. What I want you to notice here is that we have a trailing array of 14 bytes. However, at runtime, this array can go all the way up to 255 bytes. So this was actually the reason why building object size couldn't determine the size of any trailing array. Because what happened is that compiler people, they knew that a lot of C developers, they were running into these kind of practices. So they were using basically any trailing array, regardless of the size, as a potential flexible array at runtime. So compiler people, they didn't want to mess with C code bases out there. So they decided to modify, to alter the behavior of building object size. Right? So that's the reason why this building compiler function was refusing, and that is the word, refusing to give us the right information about the size of trailing arrays. So yeah, for compiler people, this was a feature. This was not a bug, but they actually acknowledged the fact that well, they knew that this was a common practice, so they decided to alter the functionality of not only of building object size, but also of another important building compiler function that we are going to review, which is building dynamic object size, right? So they knew about this. Okay, but we needed to do something about it. I mean, we couldn't just stop there, right? So it turns out that we could do a lot of things, different things on two different fronts. So first, on the compiler side, this building object size function needed to be fixed, right? However, in order to be fixed, we also needed a new compiler option, basically to help the compiler distinguish between an actual flexible array and a fixed size array, right? And because this is something that before the creation of strict-flex-arrays was not possible. So yeah, that is why the strict-flex-arrays compiler option was created to actually fix that ambiguity, because the compiler was not able to determine when we wanted to use a trailing array as an actual fixed size array or as a flexible array member at runtime, right? Okay, so on the kernel side, what we needed to complete was the work of flexible array transformations, right? So at that moment, we realized the importance of actually completing this work. And yeah, again, this took us like 5 years to complete. And well, now let's review how the strict-flex-arrays compiler option works, so you know exactly what changed at the time. So this was released in GCC 13 and in Clang 16. We have different level values, right? So the default value, of course, is 0. In this case, everything remains the same. So if you happen to write a trailing array of any size, the compiler is going to treat this trailing array as a flexible array, right? So nothing changes. Okay, in mode 1, things start getting interesting because in this case, now when we enable this compiler option with this level value, now the compiler is going to, we are telling the compiler that any trailing array of a fixed size should be treated as a fixed size array. It should not treat these types of objects as if they were variable length objects at runtime, right? And now this behavior is only going to be restricted to 1-element arrays, to 0-length arrays, and of course to C99 flexible array members. And in this case, well, we gain bounce checking on trailing arrays of fixed size, right? So we are making progress. Okay, level value 2, what happens here is that now we restrict variable length objects to only 0-length arrays and flexible array members. So now, if the compiler notices a 1-element array, it is going to treat this 1-element array as an object of size 1 element, right? And the idea of having different level values was with the intention of doing some gradual changes in NEC codebase, right? So if you know that you've been using trailing arrays of any size as flexible array members, well, the idea is that if you enable strict flex arrays with level value 1, is because you have already fixed all those issues, right? And probably you are going to still using, or you're going to continue using 1-element arrays and 0-length arrays as variable length objects. And if you enable this compiler option with level value 2, is because you already fixed the issue of 1-element arrays, right? However, this is funny because actually transforming 1-element arrays into flexible array members is way harder than transforming 0-length arrays into flexible array members. So, in my opinion, this is a little bit backwards. So first, I would ask for people to transform 0-length arrays into flexible array members, and then after that, if they have enough manpower or developer power, I'm sorry, they could go ahead and try to transform 1-element arrays into flexible array members, because that is way harder. Okay. So with this, we gain bounce checking on 1-element arrays, and we are left with a case of 0-length arrays, right? Okay, so probably the next sensible thing to do is to have level value 3, right? Yeah, but at the time, Clang developers, they had different opinions about this. They didn't want to implement level value 3. And the reason for that is because in Clang, there is this other compiler option, this one, that if you build your kernel with Clang and you enable this compiler option, the compiler is going to report warnings for any instance of a zero-length array, right? So for Clang developers, zero-length array shouldn't actually exist because they are not part of the language. Actually, zero-length arrays were introduced to the language in the early 90s. And what they wanted us to do was to get rid of zero-length arrays in the Linux kernel. So instead of going ahead and implementing strict-flex-arrays in level value 3, they were asking us to remove these types of objects. The problem is that in the kernel and basically in any other C code base, zero-length arrays are actually useful because there is going to be the case where we are going to have arrays that under certain configuration, they are going to be, I don't know, of 100 bytes, but under certain other configuration, that array is not going to be used. So that is going to, the size of that array is going to end up being 0, right? And that is one of the cases where zero-length arrays are still useful, are still being used in any C code base. Another case where people use flexible arrays, zero-length arrays, is as markers in structures. So there are a lot of cases where people write these monstrous structures of hundreds of members, and they are actually marking the beginning and the end of certain group of members. What you would do is you would use a through group instead, but there are a lot of those cases still out there. So the thing is that zero-length arrays are useful and they are here to stay. So at the time, we were arguing with Clang developers about this. Fortunately, this issue was promptly resolved. They understood this, and they actually ended up implementing the strict-flex arrays in level value 3. So, yeah, when we enable, in the kernel, actually, this is the option what we use because it's the strictest one. So with that, we fix basically all the issues we had with fixed size arrays, right, as training arrays. So if you enable this compiler option in your code base, the compiler is going to treat only C99 flexible array members as variable length objects. So any other training array of any other size is going to be treated as an array of a concrete size. And that is important for the effort of hardening memcpy, because now we can effectively use memcpy to sanity check any training array of any size that is not a C99 flexible array member. Okay, so now let's get a little bit into the details of flexible array transformations and let's see some of the problems we ran into at the time. So I'm going to explain why this is not that simple. It's not that simple to do. Okay, so at the time, we decided to classify one-element arrays and zero-length arrays and call them fake flexible arrays, right? Because those were the most common types of arrays people were using as variable length objects. And of course, the true C99 flexible array members. Okay, so the problem with one-element arrays is that we can run into off-by-one issues. Usually, when we use a one-element array as a variable length object and we allocate certain heap space for this object, we need to take into account that the size of this array is contributing to the size of the flexible structure, of the fake flexible structure in this case, right? So this is how you would allocate heap space for a one-element array as a fake flexible array. So if you notice here, we have count is going to be the number of items we want a flexible array to have. However, we need to remember to subtract 1 all the time because the size of the size of the one-element array is already contributing to the size of the strict-flex. So we need to remove that from size calculation. And at the moment when I was doing this work, I used the array bounds compiler option in level value 2 because I noticed that when we use this compiler option, this helps us to detect all the instances of code where we are actually accessing these types of objects beyond the index value of 0, beyond the first element, right? So in this case, if we access the one element array through the index 0, the code is fine. But if we run into the case where we are iterating over these types of objects, and we access the index starting with index 1 or greater, the compiler is going to complain. So at the time, I used this compiler option to detect all those cases and focus on those issues, right? So that was my strategy at the time. But that was really time consuming. So this is the type of warning you would see if you try to implement the same strategy. Okay, the case of zero-length arrays, this is, as I was saying, they are not part of the language. They were introduced in the early 90s. And well, one important difference is that, contrary to the case of one-element arrays, the size of these arrays, they don't contribute to these arrays don't contribute to the size of the containing structure, right? Because basically they are objects of size 0 at compile time. However, they're still buggy because when I was doing this kind of transformations in the kernel, I ran into a couple of cases where people were applying the size of operator to this zero-length array, and that operation is always going to be 0. But they were using that the result of that operation in other computations. So I detected a couple of bugs there, and yeah, it was important to fix those. So another problem we run into when doing flexible array transformations is the case of UAPI. So that is a different beast because, well, in kernel code we could replace this one element array with a C99 flexible array member, and of course that is going to affect the size of the containing structure. But when it comes to UAPI, if we do that, of course, that is going to have an effect on user space code. So probably we are going to break a lot of user space code. So we cannot simply do that. So we needed to come up with another strategy. And of course, we never break user space, but as Greg Harman says, we don't do that on purpose. But of course, we do it, but we fix it as soon as possible. Okay, at the time I was using this strategy. This was horrible. Fortunately, in recent times we use something different. But at the time, what I was doing, I was basically duplicating the whole structure. And what is going on here is that the first part of the union is the original structure in UAPI. The idea is that user space is going to continue using that part of the structure. And in kernel space, we would use the flexible array, right? That's the idea for that change. And probably there are still like a couple of instances of code that looks like this in the kernel, and I need to go and review it and change it because I don't really like it. But that was what we had at the time. Okay, so instead of that, what we use now is the declare flex array helper. So instead of using this horrible union, we would have just a more simpler one. And what happened here is that we cannot simply use a C99 flexible array member in a union, because that is not, at the time, that was not allowed by compilers for some strange reason that we really didn't understand why. But this is about to change. New versions of GCC and Clang, they are going to allow for this kind of code construct. So, so yeah, this is going to change. Okay, so instead of that, we would use declare flex array. So let's review the internals of declare flex, and let's see how this is, I don't know what to think about this. It's funny, it's horrible, it's strange. Yeah, I mean, the thing is that at the time, compilers didn't allow for the inclusion of flexible arrays in unions, but they allowed for the inclusion of flexible structures in unions. So what we did was to create basically an empty flexible structure, right? And this is a trick. This is a trick that actually this tricks the compiler into believing that the code is sensible and correct. And it's correct, but it's not that sensible, right? Okay, so that's the internals of the clear flex array. Okay, so yeah, we've enabled strict flex arrays in level value 3 in Linux 6.5. That was a great accomplishment. We were really happy because, as I was saying, we run into all sorts of problems with false positives and trying to trick the compiler into believing something. Also, there is a case of the social interaction with maintainers. In the Linux kernel community, there are different subsystems, of course. In every subsystem, they have their own idiosyncrasy, so they have their own way of doing things. So what applies to one subsystem doesn't apply to other. So yeah, you need to accommodate for all that. And well, sometimes people just, they don't want your changes for some reason, or they are not in the right move. So yeah, you need to be very patient, you need to be persistent, and you need to bite your tongue a lot. But yeah, that's the way it is. Okay, so yeah, so with these changes, only C99 flexible array members are going to be considered dynamical in size at runtime. So yeah, the train array ambiguity is gone from the Linux kernel. And yeah, we gain bounds checking on fixed size arrays, finally, right? After years. So yeah, this is a long presentation. Let me take it. Oh my God. Okay, so let's continue. Okay, so now what about flexible array members? Now that we fixed the problem with training arrays of fixed size, and we remove the ambiguity from the kernel, what about flexible array members? Okay, well, this is fixed with the implementation of the new counted by attribute. So this was released in Clang 18 and in GCC 15. Bill Wendling is a Google employee. He's a Clang developer. He's basically implementing all the hardening features we've been using over the past 6 years in the Linux kernel on the Clang side. On the GCC side, Xin Zhao is the rock star there. Those two people, they are amazing. I mean, we have in the Linux Kernel Self-Protection Project, we have every other week we have meetings with them. So we are in close contact, and we share with them our concerns. We test their code. We report issues to them. So they are very, very active members in the Linux Kernel Self-Protection Project. Okay, so this is the syntax you would use for to implement this. To add a counted by annotation to a flexible array member. So what's going on with this attribute is that when we annotate, well, let me go to the previous slide. If you notice, we are going to pass the counter member to the counted by attribute. So this is a way to link a flexible array member with that member that at runtime is going to contain the information about the size of the flexible array, right? So we are actually linking that information. And well, yeah, this is basically the compiler documentation. Again, is going to help us to point to that member that's going to contain the number of items our flexible array member is going to contain at runtime. And this is where the other built-in compiler function comes into place, right? So that information is going to be available via built-in dynamic object size, right? So this is what we would use to get the size of a flexible array member at runtime. So instead of building object size, we would use building dynamic object size. Okay, So, of course, in the kernel, we have helpers for everything because the syntax is pretty horrible. So yeah, instead of that, we would annotate flexible structures like this. So this is what you go and take a look into the kernel, into kernel code. This is what you are going to see, right? Okay, so yeah, now in memcpy, we need to make the change. Instead of using building object size, we now are using building dynamic object size. And yeah, with these changes, we gain runtime bounds checking coverage on flexible array members. So the work of annotating flexible array members with a counted by attribute is an ongoing effort. So we've been doing this over the past probably 2 years. Yeah, since last year we started doing this. We continue doing this work. So now, if you build your kernel with config fortify source enable, you are going to gain all this fortification that we've been talking about. And yeah, with that, we gain bounds checking on flexible arrays. So how this works is that what's going to happen is that the code is going to be instrumented, right? So when we annotate a flexible array member with a counted by attribute, the compiler is going to instrument every place in the kernel where we are accessing the flexible array, and it's going to check against the counter if we are accessing this object within its boundaries, right? This is how this works. And yeah, of course, we made this change. Okay, now the last year I wrote a blog post about how to use the counted by attribute in any C code base, and I use kernel code as examples. So that is the link to the blog post. We're going to review one example, but you go and take a look at the blog post. There are a lot more details. Okay, so there are two important requirements to use a counted by annotation. One is that the counter must be updated before the first access to the flexible array, right? Otherwise, the compiler doesn't know, doesn't have the right information to check the size of the flexible array. The other one is that, well, at all times, the flexible array member must contain at least count members, right? Or count number of items. So this is kernel code. This is an example. In this case, well, we have our counted by annotation. Data length is going to be the counter, and then we have this patch. So if you notice here, originally, well, here again, this is the flexible array member and our counter, right? So let's review the original code. The original code, of course, we are allocating certain number of bytes for the flexible structure together with the flexible array. Then at the end, we are writing certain data into the flexible array, but after we write into the flexible array, we are updating the counter, right? So this is wrong. So this violates one of the requirements we have for to use counted by. So the update to the counter member should be first. So that is what the patch does.
Will the compiler complain about this?
Yeah. The compiler reports a warning there. So the patch. Well, you notice I just changed. I just used struct size, but the important change is this. Instead of updating the counter after the memcpy, we update the counter first. So that's a simple example of how you would use counted by. So again, similarly to the case of flexible array transformations, it's not as simple as just annotating your flexible array member. You need to review your code, and you need to comply with the requirements, right? And over the past couple of years, we've been making mistakes. We annotated a few flexible array members, and we didn't realize that we needed to modify other pieces of code, right? So maintainers were really pissed off about it, but that is fixed now, of course. But that is something that is fairly simple to miss. But yeah, we need to take that into account. Okay, so now what's next is, we are going to have counted by annotations on pointers. This is coming. Actually, this is already out in Clang, because right now we are in Clang 21, I guess. And this is coming in the next version of GCC. So yeah, we're going to be able to annotate pointers, and yeah, that is going to be amazing. Okay, so up to this point, we have reviewed the evolution of bounds checking in the Linux kernel, the work we've been doing in the Linux Kernel Self-Protection Project over the past 6 years. I mean, again, it's been a lot of work, a lot of social interactions with a lot of people, a lot of back and forth, some fights, a lot of frustration. But in the end, the outcome is, is good, right? So now let's review something I've been working on over the past year. This is bleeding edge Linux kernel hardening. So there is this compiler option, Wflex-array-member-not-at-end. It was implemented by Xin Zhao in 2023. And well, let's remember that one of the requirements to use a flexible array is that it should be the last member in any containing structure, because if we have more members after the flexible array, we are going to override those arrays and those members, and that's undefined behavior, and that's a bug, and we don't want that, right? So that is why this is enforced by the compiler. So what this compiler option does is going to report issues when we have instances of a flexible structure in the middle of other structures, right? Because if we have instances of flexible structures in the middle, then we have flexible arrays in the middle, right? So that is a problem. That is something that we want to correct. And well, when I build a kernel with this compiler option, I ran into more than 60,000. More than 60,000 of these warnings. And of course, those are no unique warnings. Only about 1% of those are unique warnings, which accounts for 650. But still, there are hundreds of warnings, which in its vast majority, they are false positives, of course, right? But actually, I have found a few actual bugs. And that is why we want to enable this compiler option, because it's useful. It detects issues, it detects bugs, and it's fairly simple to introduce problems, right? Actually, I'm going to give another presentation 10 minutes before 4 p.m. today, where I'm going to be talking for 40 minutes about what I am doing to address these issues in the kernel. So if you are interested, come to my presentation in a few hours. Okay, so just real quick, when I was reviewing all those 650 unique issues, I managed to classify those into 4 different categories. Those are hyperlinks. You are curious and you want to take a look. If you don't want to come to my presentation later, you can just take a look at those issues. And yeah, it's really interesting. It's not that simple. It's been a lot of work, but yeah, this is something that I've been working on recently. Okay, let's jump to the conclusions. Okay, so we had the problem of bad vibes like bugs, bad vibes like vulnerabilities, and we also had the problem with unintentional cross-member overflows, right? So that is fixed if we update memcpy to now use building dynamic object size instead of building object size, of course, in mode 1. Then we had the problem of intentional cross-member overflows. Okay, that is fixed with the adoption and the implementation of struct group. So with struct group, we fixed all those false positives. Then we had the problem of training array ambiguity, right? The issue with the compilers not being able to distinguish between trailing arrays of a fixed size and trailing arrays as variable length objects. So that is fixed with the flexible array transformations. We need to transform every single instance of one-element arrays and zero-length arrays into C99 flexible array members. And we need to enable strict flex arrays at the strictest level value, which is 3. Then, of course, we had the problem of lack of bounds checking on flexible arrays. That is fixed with counted by annotations. And, of course, with the use of building dynamic object size. This is something that if you are an embedded software developer or you have your own pet C code project, you can actually use that kind of annotations because they are out in GCC 15 and Clang 18. And well, we still have the problem of bounds checking on pointers. That is going to be fixed with counted by pointer, which, by the way, this is not an attribute. This is a helper, because the attribute is the same. The attribute is counted by. However, we needed to distinguish. We needed to use a different helper because the functionality. The functionality to add counted by annotations to pointers is going to be released in the next version of GCC, right? So we need a way to distinguish between compiler versions. So if you use GCC 15, you cannot use counted by pointer, right? But if you use GCC 16, the next version, or if you build your kernel with Clang 20 or Clang 21, which is the latest version, you are going to be able to use this helper, right? And well, we still have the problem of flexible arrays in the middle. But that is going to fix when I finally enable this compiler option. This, of course, is work in progress. Hopefully, I'm going to be able to finish this work in the next 6 months. Let's see. OK, so yeah, so now I have a clear strategy on how to address this problem, and how to enable this compiler option. And well, you build your kernel with config fortify source and config UB bounds. Which, for those who don't know, UBSound stands for undefined behavior sanitizer. You are going to gain all this fortification, right? And well, I want to think that over the past years, we've been improving the security of the kernel significantly. And with that, thank you. I added some resources at the end, so you can take a look when the slides are available. You can take a look at that. So yeah, you have any questions? I don't know how we have time. No? I don't know. Perfect.
So why did you decide for a struct group instead of splitting up the memcpy into 3 memcpy calls to each?
Well, that's precisely for the same reason that people didn't want us to use substructures, because for them that's like too much changes to the code, like adding too much lines of code.
Okay, that's my age here.
Huh?
Yeah, I would have seen it different, but that's what you said. People see things a lot different.
Exactly. Yeah, depending on the subsystem, some people they don't care, but other people they don't really like if you modify one line unnecessarily, right?
That's what
on their view.
Okay. Wow.
Yeah.
Hi. Really interesting talk. Thanks. So this obviously involves like changes to the compiler and new flags and features and stuff. I'm presuming at first you can just enable that for yourself. What's the policy for like that filtering in to make it into one of these options or make it mandatory? Is there a defined flow for that? What happens with that? Or as in, at some point, do you want everyone to be building this as a default option? Yes,
exactly. No, yeah. Everything I've been talking about here applies to the whole kernel. We want to enable all these hardening mechanisms across the whole kernel tree.
Right.
So the compiler options, they are supposed to be enabled in the main make file, right?
Okay, but when does that actually happen? At what point do you say?
We finish, okay, yeah. After we fix every single false positive caused by any of these options.
Oh, okay.
At that point,
just everyone building just has to have the new compiler.
Yes.
Okay, fair enough.
Yeah.
Thanks.
Yeah. Here, please.
Hi. There are flexible array members in the kernel that are not counted, like
Yes.
say null terminated.
Yeah.
How are you going to deal with them?
Well, you need to annotate them. Yeah. Yeah, you need to add the counted by annotation.
Oh, yeah, but my question was, are there those members that are not counted? They don't have any counter member.
Oh, they don't have a counter member.
Right.
Oh, okay. Yeah, okay. I mean, ideally, whenever you are going to implement a flexible structure, ideally, you need to include a counter member. Or it is advisable to include a counter member. But yeah, we have a lot of those cases where, yeah, there is no counter member. Right now, we cannot annotate those flexible arrays for obvious reasons, but the solution in that case would be to try to first include a counted member. But we need to be careful because if we are talking about hardware structures, right? I mean, sometimes that is not possible, right? So.
Right. Yeah, what I was thinking about was, for example, flexible array of type character. Then you can obviously do null termination. That is just 1 byte, as opposed to you have size, then you'll waste 4 bytes.
Yeah, sure. Yeah. We have those cases too. Yeah. So, any other question? So. Yeah, so again, I mean, I'm going to be talking about the last compiler option for 40 minutes in a couple of hours, 3 hours. If you are interested, it's interesting to see all of the things people do to accommodate flexible arrays in the middle, because they do that intentionally, right? And my work is to modify that code and to fight with people, and I'm going to explain how I am doing that. Okay, thanks.